Okay, before we continue, I just want to draw your attention to some quite useful diagrams, I think, in the Hitchhiker's Guide in section 3.7. So in connection with Curry-Howard. So there's this table here at the top that indicates the equivalence between tactics, structured proofs, and raw proof terms. So it's approximate list because, of course, tactics work a bit differently than structured proofs. They're backward instead of forward. Nonetheless, there's a quite strong correspondence. If you forget about apply, which is the key tactic that goes backwards. So an intro in tactic corresponds to a fix in a structured proof, which corresponds to lambda in a raw proof term, and so on and so forth. So you see the have. Well, in lambdas, you don't need have, right? So if you can just use a lambda applied to an argument, and you see the argument h here will go into the k, and then inside the body, here, the three dots, you can have whatever follows the have. And same thing with the let, except that it's going to be data instead of a proof. Okay? And you know, the show, you can do much more concisely here. You can just put the h or h colon p if you want to specify the type, and all three have calc. So I think that's a nifty little summary of the three main styles that we've seen so far. And again, I think most of you will probably go for the tactical style, but it's entirely up to you. And then the other diagram is quite interesting because it tries to dispel some confusion that arises with terminology. So when we talk about types, when we talk about terms, proposition, proofs, you know, what do we mean? And we can mean different things, and this diagram sorts everything out. So first, you'll see that several terms are, well, at least terms and types are defined twice. So you have really terms in the strict sense, and you have terms in the wide sense. So in the wide sense, everything is a term. You know, any expression you type in Lean is a term. And a type is any expression that can be on the right-hand side of the column, right? For example, natural numbers here is a type. It's also a term because everything is a term. But 2 plus 2 isn't a type because it can never appear on the right-hand side of a column. So here we see some symmetry between the terms and the proofs, right? And the types and the propositions. That's the PAT principle. But what I should say is that the proof here is also a term. You know, because everything is a term, and the proposition here is also a type because everything from here on is a type. And then everything from here on is a universe. And so we see the word types occurs once, twice in this diagram, and 3 times, right? So type with a big T is the type of types in some sense, but types that are not propositions, like prop here, right? So it's basically a universe, and it's called type with a big T. So we'll just call it big type if we need to refer to it. It's the type of, you know, things that we normally would consider types, whereas prop is a type of the things we would normally consider propositions. Okay, so I mean, this diagram is useful for reference. You don't have to memorize absolutely everything I just said now. I'm also not going to ask at the exam to fill in the things, because again, this is a practical course. But if you're confused at some point, what is meant here by term, what is meant here by type, you can look it up. And now we can continue with what I really wanted to talk about, which is induction by pattern matching. And to do that, I need to switch screen. Let's see if I manage to do that. There we go. Right, so now we should be following VS Code. Right. So here I just want to teach a little trick that you know, some students like. It's quite idiomatic in Lean. It's an alternative way to perform inductions using pattern matching, exploiting Curry-Howard correspondence. So we're not going to do many proofs of that style in the course, but I think it's very interesting and you know, for some people maybe mind-blowing even. So I always had this idea that a good way to teach induction to computer scientists would be to ask them to write a program, right? So suppose you want to prove a property P for all n. You could take n as argument, and your program would print a proof of P of n, right? So you pass 3, and it prints a proof of P of 3, by doing, the base case, and then the step once, and then the step a second time. It would glue together as many steps as it needs, a kind of template, right? It would generate on the fly the proof that you need for the n that you want. And that program would essentially be a proof by induction, right? So proof by induction is the mathematician's way of writing a program that takes an n and iterates the induction step n-1 times, and then applies the base case. So I thought that would be a nifty way to teach induction. It turns out I wasn't the first to have this idea. So it's with Curry-Howard, it's a very natural thing, right? Because proofs are terms. So if you write a recursive program, then you can use it as a proof by induction. So I'm going to show how, right? So we start with the reverse operation, which takes a list and turns it around. I think we defined it in lecture 1 or 2, 1 even, yeah. Okay. And then we have here the version with pattern matching. And here it's very important to explicitly state the for all x, for all y. You cannot have them as parameters. You cannot put them on the left-hand side of the column if you want to pattern match on them. So you say for all x, for all y, then you have your property, right? You see that the reverse of append is the append of the reverses, but you have to put ys before xs, right? It's a very intuitive property, right? And then we do pattern matching. We have two variables we pattern match on. So we have two columns here, and in Lean, we tend to try to align them as much as possible, but you don't have to. So we start with the empty list. So you see we're doing pattern matching just like as if we were writing a program, as if we're writing a definition, and these would be the arguments to the program, right? Except if it were a program, then typically we would have this arrow instead. We would say, well, we take a list alpha, and then we take a list alpha, but the problem is we couldn't refer to them here. We need a dependent type. But you see the syntax we've seen with def. This was a recursive function definition. And now we're doing the same with the lemma. Lemma and def are almost the same thing. Again, because of Curry-Howard, there's no need to make a big distinction between the two. We can consider that they're exactly the same, actually. It's just there's really a tiny operational detail that doesn't concern us. That's different. I don't even entirely know what it is. Okay, so but it's related with the fact that once we've defined the lemma, we don't care so much about the proof. We only care about the fact that there is a proof. Whereas when you find a function, we care about which function we've defined. So there's this asymmetry that we will come back to in lecture 11 between data and proofs. Okay. And now, right, so I can, this is the skeleton here. We see, oh, I need to return something of that type, which means a proof of that lemma. And here, another one, so the step. And well, let's start, so the base case is easy. You see, it's just a simplification, and we pass the definition of reverse. So that's easy. Here, that alone would not suffice, because we need the induction hypothesis. So what is the, so let's expand this proof to see something. I always recommend to use begin during proof exploration, begin and end, and once you've found the proof, then you can compress. Right? So, okay, we apply sim, put a comma, very important, so that we see what's going on. And now we see there's something here on the left-hand side that matches the left-hand side of the induction hypothesis. We don't need too much to worry about these quantifiers. They'll get instantiated automatically. The XS, will they? I don't think, no, they will not, because they're in round parentheses, right? So what we can do is we can write a have to debug what we're doing. So we can say, let's just, what we want to do really is apply the induction hypothesis. And the induction hypothesis is the lemma that we're proving, right? So we can use, and it has the same name, so we can do a recursive call to the lemma that we're proving, right? So if I just add it like this, then it's happy. However, that's a bit dangerous. There's always the danger that you use the lemma to prove itself without doing any recursion, right? By having the exact same same values as argument. Like here, for example, here it complains there are unsolved goals. Okay, yeah, it just didn't work. Sorry, but the point is we want to avoid infinite recursion. We want a program that terminates. Right, and indeed, Lean absolutely requires a program that terminates, because if you say, "Oh, I know how to prove 0, and I'm going to call myself because I know how to prove 0, and I'm going to call you get the idea." So we have to be a little bit careful, and the best way to be careful is to add explicitly the arguments. Right, we're doing a recursive call. We drop the x. We just want the xs and the ys. Maybe it will be clear if I show the goal again, right? So here I have xs, I have ys. This is what I want to pass in there. So I pass them explicitly, and then I'm sure that it will apply the lemma in the right fashion and not apply it too early to the entire goal, which would be the equivalent of doing this basically. Right, and that would be catastrophic. So I'm not sure if I can produce the error here. No, okay, but doesn't matter. Sometimes it happens. Okay, and this is the version with the induction prime, so we can do it. I don't know if I've talked about these case labels, but they're just for, well, they're for documentation, so I could remove it, right? And also for renaming the variables if we want. Although in this case, I think the default names are quite good. So I could write it like this. Okay. And this is another example. This is a favorite. The reverse of a list is the empty list. And you see, once we have reverse append, then it's very easy. And we have, you see, a recursive call here again. So this is the induction hypothesis. And if we don't pass the argument, we're fine, but we're still not going to risk it, right? And that's it. So this is a technique I'm showing mostly for your own culture, I would say. We're not really going to build on it. It has some disadvantages. In particular, it will not work well in lecture 5 when we're going to see a mechanism called inductive predicates. For that reason, I generally recommend that you use induction prime for all of your inductions, but if you want to try this one and use it once in a while and you find that you like it, I'm also not going to stop you.